Hey there, it's Shannon Magic Myers, ready to talk about some mathematical induction. My favorite way to visualize mathematical induction really is by using dominoes. I found this kind of really cool video here on YouTube. Pretty awesome, huh? All right, so anyway, the idea being that if we had infinitely many dominoes lined up in such a way that if any one domino falls backward, the domino behind it also falls backward. Now envision what would happen if the very first domino fell. Well, they'd all fall, just like we kind of, saw in those clips. So mathematical induction works in a similar manner. If some property is defined for integers n, and it is true for some fixed integer, and we could also show that the property was true for the next integer, then it is true for all integers greater than the fixed integer. All right, so the method of proof by mathematical induction, there's actually a principle as well, but it pretty much kind of repeated this, so I only put this in the notes. Consider a statement of the form for all integers n greater than or equal to a, some property p of n is true. So to prove a statement like this is a two-step process. You have your first step, which is called the basis step. And then you show that whatever the first integer is, you show that P of A, I'm going to say, is true. It often starts at 1, but we'll just call it P of A. And then our inductive step, show that for all integers k greater than or equal to a, if P of k is true, then P at k plus 1 is also true. So to complete this step, what you need to do is suppose P of k is true, where k is an integer and k is greater than or equal to a. This supposition is called the inductive hypothesis. Then you just show that P at k plus 1 is true. So really with mathematical induction, the goal is to stay organized, all right? So let's take a look at this theorem here. The sum of the first n integers. For all integers n greater than or equal to 1, it turns out that 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 all over 2. Now, this is something you might want to stick in your brain when you're taking the GRE, which is the graduate record exam. They almost always have a problem like this or some version of it. So it's good to know that. Otherwise, it's a pretty long computation. All right, so here we go. Here's the proof. So, all right, we're starting with n equal to 1, so we could just say let n belong to the positive integers, right? And we're going to let P of n be the equation 1 plus 2 plus dot 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 plus n is equal to n times n plus 1 all over 2. So our basis step or evil plan, however you want to start with, first part of evil plan, is we want to show or check, if you will, that P at 1 is true. All right. So sometimes this step on one of the sides, usually the left-hand side, is so easy it's hard, right? So for our left-hand side of the equation, if we look, what is that very first term? Beautiful. P of 1 is just 1. Now, what about the right-hand side of the equation? Well, P of 1 is going to be 1 times 1 plus 1 all over 2. And I'm looking over here at, P at n on the right-hand side. That's where we're plugging in the n's, all right? So, let's compute this guy. Well, that's going to be 1 times 2 over 2, which is 1. So that checks out. If the basis step doesn't check out, then you're done. I mean, this wouldn't be true, all right? It would be a counterexample, so you'd be done. But double check where it starts, right, before you make that decision. All right, so now we want to look at the inductive step. So our inductive step, let's identify our K. So we're going to let K belong to the positive integers. And why don't we let what is our P of K going to be? It'll be the equation 1 plus 2 plus dot 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 plus K is equal to K times K plus 1 over 2. So this is kind of like we were talking about before, the dummy variables. We want to use a different variable here temporarily, all right? So next up, what do we want to do? We want to check P at K plus 1. That's the plan. All right, so the left-hand side, P at K plus 1 is going to equal to, so now we're using just that string of numbers that's right above it. So 1 plus 2 plus dot 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 plus K plus 1. So wherever we saw K, we're putting in a K plus 1. Good so far? Okay, but couldn't we also write this as 1 plus 2 plus dot 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 plus K plus 1? Because K plus 1 is just the integer right after K. Cool? All right then, well, isn't this here 1 plus 2 plus dot 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 equal to P of K? And what was P of K? Awesome. P of K was this here. Groovy? All right. So that's really one of the big tricks of using mathematical induction as a tool. Oh, and let me finish, sorry. Plus our K plus 1. I'm just keeping it grouped so you see the difference. All right, so then what was P of K? It was K times K plus 1 over 2. And then we're still adding our K plus 1. Well, in order to add that, we want to get a common denominator, right? So when we multiply numerator and denominator by 2, we will get K squared plus K. So I distributed the K through the top two factors in the first term, and then plus 2K plus 2, and that's distributing the 2, and it's all over 2. Good so far? All right, then we'll have K squared plus 3K plus 2 all over 2. But doesn't this guy factor? It does indeed. It factors as K plus 1 times K plus 2 over 2. Groovy? All right, so you're done temporarily because that's just the left-hand side. Now we want to make sure that the right-hand side yields the same result. So let's start work on that. The right-hand side is P at K plus 1. Well, when we do P at K plus 1, we're going to get K plus 1 times K plus 1 all over 2. And I got that from this one over here. Cool, cool. All right, so, and what is this one? This is going to equal to, beautiful, K plus 1 times K plus 2 over 2, which is what we got for the left-hand side, right? So we're all done. We have verified this property. And typically, when you use mathematical induction to verify a property or to show a property is true, it's often called an axiom. All right, so now let's look at a definition here. This definition relates to closed form. So if a sum with a variable number of terms is shown to be equal to a formula that does not contain either an ellipsis or a summation formula, we say that it is written in closed form. And so I didn't really emphasize the name of the symbol before, but if you have any sort of dot, that it represents an ellipsis. And remember, we've seen them, in between commas. We've seen them in between products. We've seen them in between plus signs. But that symbol is called an ellipsis. Okay, so let's take a look at example 1. We want to evaluate 5 plus 10 plus 15 plus 20 plus ... plus 300. Well, we just learned this formula here, right? That the sum of the first n integers is n times quantity n plus 1 over 2. So, unfortunately, it's going by fives, isn't it? So, let's go ahead and get our formula out. We know that 1 plus 2 plus ... plus n is n times n plus 1 over 2. So let's work with this sum and see if we can get it to look more like that. Cool so far? All right. So this is going to equal to, if I factor out a 5, do you see I'll have
in the parentheses 1 plus, beautiful, 2 plus 3 plus 4 plus dot 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 plus, perfect, 60. Cool, cool. And so that tells me that my n is what? Beautiful. My n is 60. So this will be 5 times 60 times 60 plus 1 all over 2. And what I'm doing is everywhere I see an n, now that I've gotten it into that format, I'm plugging in 60 because 60 is my n. But I still have to multiply everything by 5, so don't forget about that. All right, well, 2 divides this factor of 60, so we'll end up with 5 times 30 times 61, which will give us 5 times, what, 183? And that gives us, or I'm sorry, 1,830. And then that is going to give us, beautiful, 9,150. Cool, cool? All right. So that's one way you can apply okay, so the next step is the theorem of 5.2.3, which goes over the sum of a geometric sequence. All right, so for any real number r except for 1 and any integer n greater than or equal to 0, it turns out that the summation from I equals 0 to n of r to the I is equal to r to the n plus 1 minus 1 all over r minus 1. So let's prove this. So to start out our proof, we need to identify what r and n represent. So let r belong to the real numbers such that r is not equal to 1. And we can let n be a non-negative integer that takes care of including 0. And we're going to let p at n be the equation p at n, summation from I equals 0 to n of r to the I is equal to r to the n plus 1 minus 1 all over r minus 1. Groovy? All right, so now what do we do first? Perfect. We need to go to our basis step. And what are we starting with? What's our very first deal that we're starting with? We're starting at n equal to 0, right? So we need to check p at 0. Oops. All right, so for our left-hand side, be careful where you're plugging in stuff here. Remember, we're plugging in, this one's in terms of n, so we're plugging in for n. So the summation from I equals 0 to 0, because n is 0, of r to the I is just equal to r to the 0, which is equal to 1. So this is where the n's are, and that's what we got.
So for our right-hand side, and sorry, you know what? This is P at 0. So for this side, P at 0 is equal to, good, R to the 0 plus 1 minus 1 all over R minus 1. And let's see what we get. So this is where I plugged in a 0. So that will give us R to the 1 minus 1 over R minus 1. But isn't that just R? R to the 1 is R. So you get R minus 1 over R minus 1, which is 1. So that checks out. Cool so far? Alrighty. So now we'll do our inductive step. So we'll let K be a non-negative integer and P at K be the equation summation from I equals 0 to K of R to the I is equal to R to the K plus 1 minus 1 all over R minus 1. Cool, cool? Now, keep in mind our left-hand side, just so we kind of know what it looks like. The summation from I equals 0 to K of R to the I can also be written as R to the 0 plus R to the 1 plus R squared all the way to plus R to the K. Cool, cool? All right, so let's do our thing. The left-hand side. All right, so P at K plus 1 is equal to R to the 0 plus R to the 1 plus R squared plus dot 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 plus R to the K plus 1. But remember that trick. What do we like to do? We like to see what it get the first terms until your kth term, right? So we've got these going on, and so R to the K would be the term before R to the K plus 1. But what is all of that stuff? Isn't that P at K plus R to the K plus 1? So all of this stuff here is our P at K. Because P at K, remember, was this summation. So we can substitute in what P of K is supposed to equal to, right? Which is this part here. So this is going to give us R to the K plus 1 minus 1 over R minus 1, and then plus R to the K plus 1. Now, getting a common denominator, let's see what happens. We need an R minus 1 over R minus 1. Whoops. And we need to clean it up a little bit. So that's going to equal to R to the K plus 1 minus 1 plus. Now distributing the r to the k plus 1 to both of those terms, we'll have r to the k plus 1 times r to the 1, right? And then minus r to the k plus 1. All of this will be over r minus 1 because we got our common denominator. But what is this? This will be equal to, notice that the r to the k minus 1s, or r to the k plus 1s will zero out because they have opposite signs, right? And r to the k plus 1 times r to the 1 is going to be r to the k plus 2, beautiful, k plus 1 plus 1. And then we'll have what? Minus 1 over r minus 1. All right, so now we need to look at the right-hand side. So the right-hand side is going to be, so p at k plus 1 equals, so we're utilizing the formula that's circled here. I'll circle it again. R to the k plus 1 minus 1 over r minus 1. But in wherever we see a k, we're going to put k plus 1. So this will be r raised to the k plus 1 and then minus 1 over r minus 1. But what is that equal to? R to the k plus 2 minus 1 over r minus 1. And isn't that what we got for our left-hand side? Over here, where was it? Actually. Right? So groovy, we did it, and we've verified that property. All right, so another example. Let's write 3 plus 3 squared plus 3 cubed all the way down to plus 3 to the n in closed form. And n is an integer greater than or equal to 1. So let's see what we've got here. So what formula will we be using? Good, you're going to want to use the fact that I'm going to write it in expanded form, r to the 0 plus r to the 1 plus r squared plus dot 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 plus r to the n is equal to r to the n plus 1 minus 1 over r minus 1. Groovy? All right. So, here we go. 3 plus 3 squared plus 3 cubed plus dot 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 plus 3 to the n. What's that equal to? Beautiful. If I factor out a 3, and I'm factoring out the 3 because I need something to the 0 power. And remember, 3 to the 0 power is going to be 1. So I have 1 plus 3 to the 1 plus 3 squared plus dot 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 plus 3 to the, all of them went down by 1, so won't it be 3 to the n minus 1? Cool, cool. Well, now that I've started this at 1, I can just plug in n minus 1 wherever I see an n. So, in the formula. So, this is equivalent to 3 times, my r is 3, and my last term is n minus 1, so I'm going to plug that in here. And then add 1. So n for n, I'm putting the n minus 1. And then don't forget to subtract the 1, and that's over 3 minus 1. Well, that's going to give us 3 halves, because the 3 minus 1 in the denominator is 2. And then I'll have times 3 to the n minus 1. And we're all done. We've got it in closed form. No summations or ellipses. Cool, cool? All right, so next up we have just a few more examples of proofs using mathematical induction. All right, so here we go. For all integers n greater than or equal to 1, 1 plus 6 plus 11 plus 16, all the way down to plus quantity 5n minus 4 is equal to n times quantity 5n minus 3, all of that over 2. So let's do it, all right? So what do we start with? We start with our let n belong to the positive integers because it's greater than or equal to 1. And let p at n be the equation. One plus 6 plus 11 plus 16 plus dot 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 plus quantity 5n minus 4 equal to n times 5n minus 3 over 2. All right, so what's the first step? Or first, step? Well, yeah, first step, we got to do the basis step. And what are we starting with? Beautiful. We're starting with 1, right? So we need to check p at 1. All right, so the left-hand side, again, so easy it's hard. P at 1 is equal to 1, right? And the right-hand side will have p at 1 is equal to 1 times 5 times 1 minus 3 all over 2, which is 2 over 2, which is just 1, all right? And that checks out, so we can move on to the inductive step. All right, so let's let k belong to the set of positive integers, and we're going to let p at k be the equation. Oops. 1 plus 6 plus 11 plus 16 plus dot 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 plus quantity 5k minus 4 is equal to k times 5k minus 3 over 2. All right? Cool, cool? Okay, so starting with our left-hand side, we have p at k plus 1 equals 1 plus 6 plus 11 plus 16 plus dot 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 plus 5 times k plus 1, that quantity, minus 4. But what's our term before that? I mean, isn't the term before that 1 plus 6 plus 11 plus 16 plus dot 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 plus, when we looked at p at k, remember, I mean, what would the term before that one be? Wouldn't it just be 5k minus 4, right? And then we'd be adding the simplified form of the other one, so 5k plus 5 and then minus 4, starting to simplify the one quantity. So then we'll have P at K and then plus 5K plus 1. And I'm getting the P of K from here, right? All right, and then now we'll have, what is P of K equal to? Well, it's going to be K times 5K minus 3 over 2. That's what our P at K was. And then we'll have plus 5K plus 1. So that's all P at K. All right, well, getting a common denominator, if we multiply by 2 over 2 on that second term, we'll have, and then I'm going to start simplifying. So this will give us 5K squared minus 3K. And then again, multiplying through by 2, I'll have our 10K plus 2 all over 2. And this is 5K squared plus 7K plus 2 over 2. And let's factor that one. So let's see. Oh, they're both prime, the, A and the C of the quadratic expression. So let's see what we have. We've got 5K and K. So everything's being added, right? So in order to get the 7K in the middle, we're going to have our 1 here and our 2 over here. And that's all over 2. Good so far? All right, so now looking at the right-hand side, right? What will we have? So the right-hand side is what's circled here. And so P at K plus 1 is going to be K plus 1 times 5 times quantity K plus 1 minus 3, all of that over 2. So we'll have K plus 1, and then when you distribute the 5 through that quantity, you're going to have 5K plus 5, and then minus 3 will give us 5K plus 2 all over 2. But what is that? If you, commute those factors in the numerator, we'll have 5K plus 2 times K plus 1 over 2. So we've shown what we needed to show. Cool, cool? I love mathematical induction. Can you tell? Okay, so second up, for all integers n greater than or equal to 1, 1 cubed plus 2 cubed plus 3 cubed plus dot plus plus n cubed is equal to quantity n times n plus 1 over 2 squared. But you know what? I want to go ahead and, just for ease of computation, this is n squared times n plus 1 squared all over 4. All right? Okay, so let's start our proof. All right, so what do we need? Just integer n. So let n belong to the positive integers because it's just greater than or equal to 1. And let p at n equal to, be the equation one cubed plus 2 cubed plus 3 cubed plus plus n cubed equals n squared times n plus 1, the quantity squared, all over 4. And now we have our basis step. We're starting at n equal to 1. So we just need to test that. We need to check that p of 1 is true. So for our left-hand side, remember, so easy it's hard. P at 1 is 1 cubed, which is 1 cubed, which is 1. And our right-hand side, okay, so on the right-hand side, p at 1 is going to be 1 squared times 1 plus 1, that quantity squared, over 4, which will be 4 over 4, right? Because 1 times 2 squared over 4 is going to be 4, so we'll get 1. All right, so our basis step checks out, and we can move on to our inductive step. So let's let k belong to the positive integers and let p at k be the equation. One cubed plus 2 cubed plus 3 cubed plus ... plus k cubed is equal to k squared times k plus 1, the quantity squared, over 4. Good so far? All right. Oh, and just in case, I wanted to remind you where this came from. Over here, we were working with that equation, all right? And we evaluated p at 1. So now working with the left-hand side, so p at k plus 1 is going to be 1 cubed plus 2 cubed plus 3 cubed, and on until we get to, good, k plus 1, the quantity cubed. And this is equal to 1 cubed plus 2 cubed plus 3 cubed plus ... plus beautiful k cubed plus k plus 1, the quantity cubed. But then we'll have p at k, won't we, for part of that. So here, remember, this is the left-hand side for, our p at k. So we have an equivalence here. And then we still have to remember to continue with the k plus 1 quantity cubed. But remember that p at k was this quantity here. So that is k squared times quantity k plus 1 squared over 4 plus k plus 1 cubed. And then working to get a common denominator, we'll multiply by 4 over 4. And we will have k squared times k plus 1, the quantity squared, plus 4 times k plus 1, the quantity cubed, all over 4. Good so far? And now if I go ahead and factor out a factor of k plus 1 squared, I'll have, from the first part, I'll have k squared. And from the second part, I'll have 4 times quantity k plus 1 to the 1, right? All over 4. And then this is going to yield k plus 1 squared times k squared plus 4k plus 4 all over 4. And that will give us, beautiful, k plus 1 squared times k plus 2 squared, right? For factoring, work on your special factor, any factoring if you need to, all over 4. All right, so let's see what happens for the right-hand side. So our right-hand side, p at k plus 1 will be equal to, all right, so we're going again, remember, with this circled business. So, but we're plugging in k plus 1. So we will have k plus 1 squared times k plus 1 plus 1, the quantity squared, all over 4. So in for this one, I just did these guys. In for k, I put k plus 1. And let's see what we get. We'll get, beautiful, k plus 1, the quantity squared, times k plus 2, the quantity squared, all over 4. And that's what we got for the left-hand side. So we're all good. We've shown what needed to be shown. All right, so for our last example, we've got a product instead of an infinite product instead of an infinite sum, or not infinite, an nth product instead of an nth partial sum, nth partial product, I guess. So here, let's do it. So, proof. Let n be an integer and n be greater than or equal to 2. And we can let p at n be the equation (1 minus 1 over 2 squared) times 1 minus 1 over 3 squared times 1 minus 1 over 4 squared, all the way down to 1 minus 1 over n squared equals n plus 1 over 2n. All right, so let's see what we've got going on here. We'll start with our basis step. And be careful, we're starting at n equal to 2, right? So we're going to check p at 2. And when we do so, we'll have p at 2, whoops. For our left-hand side, p at 2 equals 1 minus 1 over 2 squared, which is, beautiful, 1 minus a quarter, which is 3/4. Cool so far? All right, the right-hand side is p at 2 equals 2 plus 1 over 2 times 2. So we're using the right-hand side. And that is equal to, perfect, 3/4. So our basis step checks out, which means, woohoo, we can go on to our inductive step.
All right, so let k belong to the integers and k be greater than or equal to 2. And we'll let p at k be the equation (1 minus 1 over 2 squared times 1 minus 1 over 3 squared times 1 minus 1 over 4 squared, all the way down to 1 minus 1 over k squared equals k plus 1 over 2 times k. Sorry, I'm getting a little sloppy here. All right, so now let's check it out. Our left-hand side, p at k plus 1 is equal to 1 minus 1 over 2 squared times 1 minus 1 over 3 squared times 1 minus 1 over 4 squared times 1 minus 1 over k plus 1 squared. But including the kth term, what would happen? We'd have 1 minus 1 over 2 squared times 1 minus 1 over 3 squared times 1 minus 1 over 4 squared times 1 minus 1 over k squared times 1 minus 1 over quantity k plus 1 squared. Good, good? All right, so what is all of this going to equal to? Oh. Good, it's going to be p at k, right? So we'll have p at k times 1 minus 1 over k plus 1, the quantity squared. And again, that comes from all of this is p at k. All right, so now what did p at k equal? Beautiful, it equals k plus 1 over 2 times k. And we're going to be multiplying this to 1 minus 1 over k plus 1, the quantity squared. All right, well, let's go ahead and I'm going to go ahead and get a common denominator on that second factor. And that will give us k plus 1 squared minus 1 over k plus 1 squared. And then we can divide out one factor of k plus 1. And we'll have k squared plus 2k plus 1 minus 1 all over 2k times k plus 1. So this quantity here is equivalent to this here. All right, well, continuing, we will have k squared plus 2k over 2k times k plus 1
But what is that? That's going to be k times k plus 2 over 2k times quantity k plus 1. With the k's dividing out, we'll have k plus 2 over 2 times k plus 1. And that's for our left-hand side. All right, so continuing, we will have the right-hand side. So our P at k plus 1 on the right-hand side is going to be k plus 1 over 2 times k plus 1. Remember, we're looking at the formula on the right-hand side, this one here, which is k plus 1 over 2k. So wherever I saw a k, I plugged in a k plus 1. And then simplifying this one, we'll have k plus 2 over 2 times k plus 1, which is equivalent to what we got for the left-hand side. So we are done. If you like what I'm doing, please subscribe. And I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. Bye.